Hello everyone. I am here to talk about our paper ETL, Efficient Transfer Learning for Phase Tasks. This work was done in collaboration with Isha Dua, Professor Vineet N. Balasubramaniam and Professor C.V. Jawahar. Deep neural networks are widespread in machine learning, achieving state-of-the-art results in most phase-related tasks. However, they are known to be highly data and compute hungry. Massive phase datasets with millions of images, such as VGGFace2, which contains 3 million images, or MS-Celeb1M, which has 10 million images, partially solve the problem. While large datasets exist for phase tasks such as recognition, other tasks such as age or emotion recognition have comparatively very little publicly available data due to the difficulty of collecting and annotating data. Thus, transfer learning is popular, where we take a model trained on a primary task with lots of data and transfer it to a secondary task using fine-tuning. However, the resulting model is still large and computationally intensive, and the transfer learning process is time-consuming. It does not fully utilize the learned filter information from the primary model. Through this work, we aim to solve three problems in one go: the lack of extensive data for some phase tasks, the time taken to train or transfer learn new models, and the massive size of these deep phase models. In literature, we see various examples of cross-task learning, where a deep model trained for one task learns other related tasks without additional supervision. For example, these works show that CNNs learn object localization while being trained for object recognition or scene recognition. Here we see ConNets trained for recognition, learning image correspondence and semantic parts. Coming to faces, we see that a model trained for expression recognition learns facial action units. Let us examine cross-task learning in the face domain closely. We see that faces are highly structured and the various tasks in the face domain are very similar. Can we find any relationship between face tasks? Consider this VGG16 model trained for face recognition. In its last convolutional layer, it has 512 3x3 convolutional filters. Let us determine if any of these filters respond to the head pose estimation task. We use the head pose dataset, which consists of images of 15 people at various head poses, keeping all other factors constant. We pass the dataset images through the VGGFace network and study the L2 norm of feature maps of each of the 512 filters in the last convolutional layer. We observe the response of certain filters are correlated to the yaw of the head. Some filters give high responses for faces looking straight, whereas other filters give high response for faces turning left. Thus, we see that a few of these filters learn to respond to head pose even though it has never been trained for supervision on head pose. We call these filters cross-task aware filters or CRAFs. In the rest of this talk, we will discuss how to leverage these CRAFs to do efficient transfer learning and simultaneously solve the three problems of less data for certain phase tasks, the time to transfer learn new phase tasks, and the space and time complexity of the resulting models. We aim to obtain lightweight models for related phase tasks through transfer learning, starting from a pre-trained VGGFace model. Here, recognition is the primary task and our secondary tasks are head pose, gender, age, and expression. We leverage the cross-task aware filters or CRAFs to do transfer learning efficiently. Our first step is to find the optimal set of CRAFs for our secondary task. Let us consider a dataset D associated with a secondary task. D consists of a set of images I and their associated ground truth Y. Now let us look at a layer L in the CNN having CL input channels and CL plus 1 output channels. So its weight is of size CL plus 1 cross CL cross K, where K is the filter size. When we pass an image through the network, the output of this layer L is of size N cross CL plus 1 cross W cross H, where N is the number of images. We aggregate the activations using average. We need to choose groups of filters whose activations are highly correlated with Y. One way to do this is to rank each filter group based on a correlation coefficient and pick the highest ranked filters. Individually picking filters results in a greedy solution as we do not consider the interdependence of filters. Instead of exhaustively checking all groups of filters in a layer, we use LASSO regression to find the best filter groups to predict Y. Here, beta is the LASSO regression weight vector and lambda is the non-negative regularization parameter, which determines the sparseness of the regression weights, beta. The number of filters chosen decreases with an increase in lambda as more coefficients of beta become 0. Our next step is to choose the correct lambda for each layer. Choosing a different lambda for each layer is non-trivial, as a change in lambda does not cause a corresponding change in error. So we define a global hyperparameter that balances the trade-off between sparsity and error, eliminating the need for per-layer sensitivity parameters. To see how the error varies with sparsity, we create characteristic curves for each layer, which is the plot of the sparsity of filters versus the error for different values of lambda. We train 100 LASSO models by varying the lambda. Here are the characteristic curves for gender, where each line represents the characteristic curve of a different convolutional layer. We note that the characteristic curves are flat-bottomed, requiring only a few filters for predicting gender. Here are some more characteristic curves. If we look at the graph for expression, we see that it is more curved, meaning that the information is spread throughout the filters. The shape of the characteristic curve varies with the secondary task. We define a global parameter, gamma, which is the maximum allowed increase in error. We define the knee point of the curve K as the lambda value that maximizes the sparsity while keeping the error within limits. We calculate the lambda value at knee point K for each layer using the chosen gamma parameter. Once we choose this knee point, we find all the filters for each convolutional layer which need to be kept or removed. Now that we have found our optimum set of graphs, we will remove the non-graph filters from the model to obtain a sparse model. Consider a conv layer L, which has the weight vector of size CL plus 1 cross CL cross K. The weight of the next layer is CL plus 2 cross CL plus 1 cross K. In order to remove the ith filter from layer L, the ith output channel weight is removed. The corresponding ith input channel weight is removed from layer L plus 1. We remove the filters from all the convolutional layers in one shot and multiply the filters with the corresponding beta values. Finally, we fine-tune the prune network on the secondary task to obtain the sparse transfer-learn model. Here is our entire pipeline. First, we pass the dataset images through the model and collect the activations at each layer. We then plot the characteristic curve and find the knee point for each layer. We generate a sparse model by keeping only filters corresponding to the non-zero coefficient of the regression weights of LASSO according to the chosen gamma. And finally, we fine-tune the sparse model on the secondary dataset to obtain the efficient transferred model. Now we present our results. Our primary model is the VGGFace model, which is a VGG16 network trained on the VGGFace dataset. We experiment on 4 secondary tasks. We use the Celebi dataset for gender classification and the annotated facial landmarks in the wild dataset for head pose. We use AFEWVA for valence prediction and the AgeDB dataset for age prediction. We use the following 4 metrics for our evaluations. Accuracy is the percentage of the correct predictions. We calculate the computational complexity in flops, which is the number of multiplication operations for one forward pass. The model size is defined as the size of its parameters. And finally, the inference time is the number of seconds taken to infer one image on the CPU. This table shows the comparison of ETL with gamma as 0.01 with the baseline transfer learning. The percentage reduction in metrics is given in the brackets. We observe a significant drop in model size, which leads to faster inference time with a slight loss in the model's accuracy. More specifically, we show that the ETL model retains up to 99.5% of the baseline accuracy, while reducing the size of the baseline model by 97%, thereby reducing the CPU inference time by 94%. Here we see the result of varying the gamma on our 4 tasks. A threshold of 0 indicates an unpruned network, and a threshold of 0.1 corresponds to a highly sparse network with 99% of the filters pruned. We observe that as gamma increases, the model size and the computational complexity reduces significantly, with only a minor reduction of accuracy. This means that the value of gamma controls the model compactness. Higher gamma results in fewer parameters at a possible cost to the performance. Thus, the threshold is a reliable way to tune the ETL algorithm and get the desired compromise between compression ratio and accuracy. In our experiments, we observed a gamma value of 0.01 as ideal. Let us compare the per epoch training time for various values of gamma. We observe that the training time per epoch reduces with an increase in gamma as fewer filters get chosen. For head pose, we observe a per epoch reduction of 32% for gamma is equal to 0.01. This speeds up the fine-tuning step, resulting in accelerated transfer learning. This graph shows the inference time on CPU per image at different threshold levels. The increase in threshold value results in higher real-time performance. A dramatic decrease in inference time of 90% enables the ETL model to perform inference in real time, which is important for deploying on low-powered edge devices. Thus, we have shown that our method ETL does efficient transfer learning, resulting in compact models without much compromise in performance. Thank you.